And the broadcast started.
All right, everyone. So thank you for joining us. We're going to get started in just a couple of minutes here. Everybody who has joined us already, you all are on mute. And welcome. And we are going to get started in just a couple minutes here. Thank you.
So John, are you seeing my screen?
Yes, I can.
Okay, and you're just seeing the presentation screen, correct? Not the rest of my desktop.
That's
Correct.
correct.
Excellent.
Hey, Chris,
Yes.
remind me, what is the shorthand command for presenter mode in Bluebeam?
Control L, I believe, at least for me and P.
Control L.
In Acrobat, it's Control L.
Oh, there's now a presenter mode in Acrobat. Huh, okay.
And to all of those attendees who have joined us a little early, we want to welcome you. Everybody is on mute, so we'll get started just right after the top of the hour. But want to welcome everybody who has joined. Thank you to the punctual crowd. Yeah, and Chris, I don't know if you saw the final numbers. It was great. We had something, I think it was like above 70 folks registered. It was really a nice list.
That's
Yeah.
great. I'm excited about it. Sorry for coming on so late. I've been having the worst time with my internet at home. I can't seem to get it working right.
I think it's a problem many of us are dealing with right now.
Definitely.
Yeah.
It's easier for me to pull the plug on my daughter's Daniel Tiger than it is when you got kids doing Zoom classwork, in the next room.
Yeah, I think it's outside. Xfinity says it's outside of our house. It's not our equipment. It's in the neighborhood.
Well, it is the top of the hour, but I think we'll just give it one more minute because I see a lot of folks joining as we speak here. So we'll just give it another minute. Welcome, everybody. Happy Tuesday, those of you who are on the phone. Quite the crowd we got gathering here. Folks from all corners. This is really great.
Love it.
Yeah, this is awesome. All right, it's 10:01, so I think we will officially get started here. Welcome, everybody, to today's webinar, Introduction to Daylighting. This is a kind of a cool webinar for us. We have a guest speaker, Meek from University of Washington's Integrated Design Lab is with us. He's going to be leading the webinar. So I will let him introduce himself in a little bit. Chris, can you cue us forward a little bit? I want to kind of knock these house cleaning slides out real fast for everybody. If we could take a look. I think everybody is pretty familiar with this stuff. You're going to be muted for the duration of the webinar. We might open up the mic towards the end if there's questions, but what we want to encourage you to do throughout the webinar is If you have a question, go ahead and submit it to us via the chat feature that you have there. Those questions will come into staff, and we'll pause every 10 minutes or so and try and check in on those questions and see if we can address them. Following the webinar, there's going to be a short survey we encourage you to take. We do that, we set it up like that so we're not sending you more emails than we have to after the fact. And a recording and a slide deck from today's webinar will be posted on our webpage. So, you know, if you miss something, folks always want to know, and the answer is yes, it will be available. Cue us forward, Chris, if you don't mind. I always like to remind folks, Lighting Design Lab is part of Seattle City Light. We are City Light employees, and it's City Light's leadership and commitment to customers that allows LDL to do the work that we do. So thanks, City Light. Next slide, please. So Lighting Design Lab, we reach a lot of different folks. We reach end-use customers. We work with design allies, engineers, architects, lighting designers. We work with trade allies, electrical contractors, electrical distributors. It really takes all these folks coming together. And this webinar, just looking at the folks who are joining us right now, it's a great example of the sort of wonderful composition of folks we bring together. And it's our experience that it really takes all these folks coming together to move the needle forward in a meaningful way. Next slide, please. I think this is kind of like back to the, you know, the radio sponsorship on the old radio show. The LDL, we have four core services. We like to share this with people. Many people know us because of our education and training, such as this webinar. You might have taken courses at the lab, or we might have come to you. Some people know us because the lab has been doing consults and delivering professional services for over 30 years. But we like to remind folks, you know, all those things are really tied together. We're doing technology evaluation. We're talking with folks all over the industry and trying to turn around and share that information back. So the lab's staying super busy. We have a really cool mission here. And this presentation that you're about to see today is a great example of that. So Chris, I think that's going to wrap it up for the intro slides. Why don't you take it forward?
Yeah, thanks so much, John, and thanks to the Lighting Design Lab for giving me the opportunity to present on daylighting design. It's one of my favorite topics. Again, my name is Chris Meek. I'm faculty member in the Department of Architecture at the University of Washington, where I teach classes on lighting, but I also run a research group called the Integrated Design Lab. We're located at the Bullitt Center.
Chris, we might have lost your audio. Okay, everyone, we might have lost Chris's audio, so we're going to try and reconnect him. We're actually reaching out to him already, so we're going to see if we can't hit a restart on this and see if we can't get him to join maybe through his phone line if the computer's having an issue. Thank you very much for your patience while we try and get Chris back on the line here. We're just standing by hoping we can get Chris to join. Okay, it looks like you maybe. Yep, Chris, we can hear you now. We can hear you now. Go ahead. Glad to have you back.
Okay, when did I drop out, John?
Kind of as soon as you said thanks to the Lighting Design Lab.
Oh, No. Did you see my slides change?
We see them changing now, but you dropped off right on the introductory slide.
Okay, I'm sorry. My name again is Chris Meek. I'm a faculty member at the University of Washington Department of Architecture, where I teach lighting and day lighting design, and I teach design studios, and I also direct the Integrated Design Lab, which is a organization. We're located at the Bullitt Center. We do 3 interrelated service streams of activity, one being research. So we do funded external research around building performance issues, energy efficiency, human comfort, lighting, developing tools, building metrics. We also do education and training. So we provide classes like this and other classes around integrated design and building energy efficiency and health design. And thirdly, we provide technical assistance. We work directly with architects, engineers, and owners to help them design the most comfortable, energy efficient, high-performing buildings in the region. So if you want to learn more about the IDL, you can access our annual report on our website at idlseattle.com, and it provides an overview of our activities. I've written 2 books on the topic of daylighting, one specifically to issues around designing with daylighting in the Pacific Northwest, and another that's a broader brush picture of issues of daylighting and integrated lighting design that I've gleaned from 15 to 20 years of practice in daylighting and integrated lighting. Can everybody hear me?
We can hear you, Chris.
Okay, good. I'm going to check in on that every once in a while to make sure. So the first thing I like to talk about is what is the opportunity of lighting, integrated lighting design with daylighting. And to me, I feel like we stand at an interesting point in time where we're looking at issues of sustainability, we're looking at issues of human health, we're looking at issues of looking for improved productivity. And one of the things that the research tends to point to is that lighting that is dynamic and changing is healthier, is more productive, and if it's designed effectively, it can be much more energy efficient. And a lot of the people that I've learned the most about in lighting design are people that come from a theatrical background, understanding how change of light, moods, situations, and dynamism is important to the experience of light. And with new controls technology and with our knowledge about light and health, I think we stand at the threshold of an opportunity to really rethink the way that we design light for spaces to be much more dynamic over time. And to illustrate that, I show a series of slides that come from an office that I used to work in up on North Lake Way. And this is the office in its unoccupied state at nighttime or very, very early in the morning. I took these in April on a sort of partly cloudy day when I was, for a time period when my daughter was first born, I was waking up and getting into the office really early. And here's what the space looked like when I got there about 6:30, 7 o'clock in the morning. It was dark, and I would flip on the light switch at the wall, and it would illuminate a series of drum pendants that ran the length of the office. And I would walk over and I would work in my space. There would be no one else there. I'd be working alone with one task light illuminated. And that felt appropriate to me. I was coming out of the nighttime environment. My eyes were adapted to low light levels. I was in this space by myself, and it just felt natural to come on and have just a little bit of a glow of electric light as I worked on my computer and felt the day transition into being. And we also had a pretty advanced control system. We wanted to demonstrate that when we when we moved into our space, and we had an electric lighting system that essentially had a sweep on if it sensed occupancy after 8:30. And about 8:30, the lights would come on and they would provide the ambient illumination of the space. You can see these are two T5 pendants, linear pendants, and they would light the desk, providing about 25 ambient foot candles. Get a little wall wash here, and again, we have our drum pendants providing lighting and accents in the pathway. And once the ambient lighting came on, I didn't really need my desk light anymore. So I turned that off, and we would work as a group in the office under this lighting condition. This is really our electric lighting scene, if you will. And eventually, we would start to get some daylight. We've got tall windows, we've got high reflectance values, we've got shallow section depth, all the things that you need to do to provide good daylighting. We had some blinds to control glare if we need to. And the space would start to swell and fill with daylight, and our electric lighting would start to fade off. We had a photocell in the space that would automatically dim that lighting down. And once there was sufficient daylight in there for about 10 minutes to fully dim the lighting, it would go into its fully de-energized state, which looks like this. And our electric lighting would be off, and we'd transition to essentially our fully daylit scene. So we were going from essentially totally electrically illuminated into this transition space, and then onto a fully daylight illuminated scene. Although we would selectively leave some electric lighting on here to provide some focus and depth, to provide a little wall washing and give a little contrast and punch to the walls. But for all intents and purposes, the real heavy energy consuming lighting was off. And we've gone from a very low color temperature to a sort of mid color temperature around 3100 K to a much higher color temperature, now around 5000 K toward the middle of the day. And to enable us to be pretty aggressive with our controls and flexible, we provided task lighting. So in case I needed to read something, or I needed more than 25 or 30 foot candles in the space, I could turn on my task lighting and get 100 foot candles on my work surface at a limited location. We also were subject to the rhythms of light and sunlight and diffuse daylight in the space. So we'd get, in this case, we see some patterns of sunlight coming in and changing the distribution of the space, the light in the space, making it a little more saturated, a little bit warmer, and creating that drama that reflects the change of the time of day, the movement of the clouds, all that stuff. And that's actually, a lot of daylighting simulation metrics will say you don't want direct sunlight in your space, but I find that some limited direct sunlight can be, something that enriches the space, but it becomes problematic when it when you have to be in it. So this is the experience of being in a patch of direct beam sunlight. Very high contrast, obviously uncomfortable, and that's when we have to go and adjust our blinds to ensure visual comfort. But as long as we provide access to that to people, we can get through these transitional periods where there might be some direct sunlight glare or other visual discomfort posed by the daylight distribution. But luckily in Seattle, we've got lots of ambient diffuse daylight. We're generally a cloudy climate, and the sun sort of peeks in and out of the clouds. And one of the great benefits of being in a cloudy climate is it's really good for daylighting, because the light's already diffuse, similar to the way that we want to generally use it in buildings for ambient lighting. And then we start to transition back to night. We can use our task lighting, and then eventually our lighting goes off. And we've gone through this cycle of, darkness, electric lighting, brightness, diffuse daylight, some occupant control, some change over time, and then returning to our unoccupied period. And that the presence of daylight in that space and the integration of electric lighting and lighting controls gives us an ebb and flow of light that's a lot like what we historically evolved under. And it turns out is a healthy experience of light that creates drama. It amplifies the experience and the connection to the outside, which we know is really, really important, and also saves significant amounts of energy because we're operating with the vast majority of hours with our ambient lighting either significantly dimmed down or turned entirely off. So let me check in. Does anybody have questions on that material or any issues hearing me?
Chris, the audio is good, and we don't have any questions at this point that have been sent in.
Okay, great, thanks. Yeah, if you get some bad audio, send me a message in the chat, and I'll do what I can to slow down or stop and try to fix it. I appreciate everybody bearing with me on the technical side. So, you know, in terms of daylighting design, when we look back at buildings designed and built prior to about 1940, almost all buildings were daylit. And that's because the architects and engineers that built them really were educated and learned how to design an environment where electric lighting was fairly scarce. You know, we're talking about gas lights, early electric lighting, and prior to the widespread adoption of conventional AC and HVAC type equipment. So buildings were designed to be connected to the outside for both natural ventilation purposes and to allow daylight into the space. And we see a building here that's a great example of that sort of pre-war architecture. This is the General Motors building by Albert Kahn and Associates in Detroit. And the contents of this building are the ground floor is essentially a retail kind of showroom type space for the things that General Motors was building at the time, engines, cars, other industrial equipment. And you can see that that's the deep floor plate section. That's the big block size piece of program. And we've got big double height windows to try to bring light into that space. On the upper floors, we have all private offices. And one of the things about these private offices is they wanted to give every single one of them access to daylight. And what was the best way to do that? To create a very narrow plan. So we've got a building where essentially no matter where you are, with the exception of the circulation way, you're no more than about 10 to 15 feet away from a window, which means that you're directly adjacent to a daylight source. There's no space in this building where you're 40 or 50 feet away from a window or in spaces where there's essentially no access to daylight. And that provides effective light throughout the entire floor plate, as well as the ability to provide cross ventilation or single-sided ventilation. When we get into the deeper section pieces of the building, we see that there's the addition of skylights, and those skylights are essentially happening in the bays between the big office bars. And what that does is that allows for some very direct visibility into the space. So for example, if you're standing out on the sidewalk here, looking at a window and into an interior space that's lit at 10 or 15 foot candles, which would have been the standard at the time, and you're out in 1,000 or 2,000 foot candles, or even more if it's a sunny day, what you would see was your own reflection, because you'd be looking at dark glass, or you'd be looking at glass with a significantly darker space into it. But by using skylights in the spaces between the office bars, what we do is we bring light into the back of the space beyond the 2 times the head height of the window that the perimeter glazing can reach, and provide brightness in the deeper part of that section that allows your eyes to travel to the back of the space and see much greater transparency through there. Anyone who's been involved in the design of retail lighting knows that there's a real strong goal to light the back of the retail space to pull your eye visually into the store and then all the way through it to the back of the space, so that you really can see the depth and the merchandise in the product. And this was a strategy done passively with daylight. And that happens at again, the deep floor plate section of the building. We also see that the spaces or the programmatic elements of the building or the components of it are organized in a way that reflects an approach to lighting design. So for example, we've got the auditorium, and that's a space where they had specialty lighting. They didn't want daylight in there. They wanted to have it dramatic and have lots of control over it. So that was the space that was really intended to be dark. So it's placed in the bottom floor at the very center of the building, where the one place that the building really doesn't have access to light. The other thing is we see our circulation way. Now, in a lot of mid-century and more contemporary office buildings, the lobby is a big glassy space. But at this time, and in some of our older buildings, I think the Seattle Tower is a great example. The lobby is actually an intentionally dark space, because what it's doing is acting to transition your eyes from the outside to interior daylit spaces. So again, if you're outside here in the front of this building and it's an overcast day, about 2,000 foot candles of brightness outside, you walk into this lobby and it's 3 or 5 foot candles, and your eyes slowly adjust to indoor light levels. Your pupils sort of open up and you start to be accustomed to indoor light levels. You get in the stairs or you get in the elevators and you go up to this space and you come through this corridor, which isn't very well daylit, maybe with a transom window, and you come out to these offices and maybe there's 50 or 30 foot candles in there, but by contrast, you feel like that's a bright space. So the architectural organization has essentially prepared your eyes to perceive this space as bright. Whereas if you transition from 2,000 directly to 50 foot candles, it would perceive dark. So the point being is that the architect and the lighting designers are creating a condition where the building organization is developed around the pattern and need of light in the space, and your sequence of movement in there amplifies your perception of brightness in spaces where you're trying to get that effect. Going forward into the future, what we've seen is a real bifurcation, going from the sort of the 50s into the late 90s and even beyond, where there's not a real strong connection between sort of the space making exercise of the architects and the enclosure design and the lighting designer and engineers work, which is to essentially provide foot candles in a lot of ways to make the space functional for whatever tasks it's designed for. So in this case, I like this image because it shows this window here, which is kind of a vestigial thing. It still provides a connection to the outside, maybe a little bit of view. You can see whether it's day or night. But really the lighting here is all done with electric lighting. This is when at the early inception of T12 type fluorescent fixtures that were able to deliver a consistent 300 foot candles in this drafting room. So we start to see where architects see their responsibility for using daylight and shaping their buildings to light spaces, and lighting designers and engineers really aren't thinking about the presence of daylight as part of their lighting scenes, and these things start going in parallel path, creating buildings that don't really respond to daylight. And in recent days, we've discovered that that's problematic for a lot of reasons. One, it's not very energy efficient to have lots and lots of electric lighting burning when there's plenty of daylight available outside. And two, it turns out that photobiology and our experience of light throughout the day is really important to regulating our brain chemistry for both wellness and health. A good way to think about that is at night, our ancestral pattern of light was to be in near total darkness with just the access to essentially starlight or moonlight. And during the middle of the day, being outside and being exposed to very, very high levels of light in the 20,000 foot candle range of the noon on a sunny day. So this diurnal change of extreme darkness and incredible brightness. And like almost all animals on the planet, the human being evolved to respond to that change in light and dark, to really enter a dormant state at night and enter an active alert state during the day. And fairly recently, there was the discovery of a photoreceptor in the eye that essentially triggered the serotonin melatonin cycle of brain chemistry to essentially wake you up and to transition you back to a dormant state. And our current reality today essentially eliminates that big changing arc and creates a fairly flattened state of light compared to our ancestral forebearers. So at nighttime, we have electric lighting both on the street and in our homes. We're exposed to screens where we see brightness, and we are in what a lot of photobiologists would say was an unhealthily high level of light exposure during the night, and an unhealthily low level of light exposure during the day. And the primary culprit, especially during that low exposure of light during the day, is our buildings. We're in spaces that don't have access to daylight, don't have connection to views to the exterior, and are essentially alienated from that bright night-day experience. So for example, this is sort of our nighttime light level. We might catch a little bit of light in the morning when we get in our car or go catch the bus and go and sit in an office building at 30 or 50 foot candles. And we might get a little dose of brightness at night, at lunchtime when we go out and grab our lunch or go for a walk. And then back in our office building at 30 or 50 foot candles. And then another dose of brightness at the end of the day before we go home to our houses and enjoy our screens and our interior lighting and are in high levels of light that allow us to see at night, which are all beneficial. However, what this does is this essentially interrupts our circadian rhythm, the cycle of light and dark that our bodies experience. And in areas north of about 43 degrees latitude, and definitely including Seattle, there tends to be significant incidences of seasonal affective disorder, which is thought to be triggered by low exposure to light. And that peaks between sort of beginning of November and the end of February. And one of the things that happens during that time period is that is when the length of our workday starts to, or the shortness of the day starts to extend into the beginning and the end of the workday. So we don't get this little bump of brightness in the morning, and we don't get this little bump of brightness in the afternoon because we go to work in the dark and we come home in the dark. And therefore, our first sort of bump of light might be going out for lunch if we don't sit directly next to a window and get that stimulus that helps us regulate our circadian rhythm, and that can shift us off and cause all kinds of issues with depression. And it turns out that disruption of the circadian rhythm has all kinds of impacts with shift workers, with non-ambulatory care facilities, sleep disorders, and even connections to different types of cancer. So with that, we also know that our design decisions have a pretty significant impact, not only on the human body, but on the planet, in terms of, you know, everything we do in terms of energy systems that our buildings use has a negative impact on in carbon emissions and in terms of energy consumption. So we can make design decisions that help through our lighting, through controls, and through the effective use of daylighting and sun control. We can create buildings that significantly reduce the amount of energy that they consume and provide a healthier work environment for people. My office is in the Bullitt Center, which is a building up on Capitol Hill that's a net zero energy building. And it essentially has every energy efficiency technology you can think of thrown at it, from dynamic exterior shading to ground source heat pump to solar array, high performance envelope. And it has virtually every lighting control strategy you could think of. The whole building is virtually day lit. So we have day lighting photo control sensors throughout the building. We have at the time, what at the time was a really, really low lighting power density at about 0.4 watts per square foot of ambient lighting, or total lighting power density for the office spaces. And comprehensive sweep controls, vacancy sensing throughout, the whole 9 yards. And yet the modeled energy performance of the building was still the single largest lighting energy performance was, or the lighting energy consumption, I should say, was the largest single end use in the building model. Now, in reality, it's a little bit less than that, and that's primarily because Dennis Hayes, who's the president of the Bullitt Foundation, goes around and turns everybody's lights off and provides peer pressure on them. But ultimately, most of the building occupants turn off their electric lighting more than the controls would suggest that they should. But suffice it to say, even in the most energy efficient buildings, lighting is still a significant component of the energy end use, despite being mostly LED. So let's take a quick break and see if there's any questions that people have, or comments that anybody wants to make. I'm trying to look at the chat log and see if there's anything there.
Yeah, Chris, we haven't had any other questions come in, but the audio is great. And I guess we can use this as a reminder. If you have questions, please type them into that chat log and we'll address them when we take these little pauses.
And John, are people able to unmute themselves and ask questions if they want to, or do they come in on mute?
Yeah, everybody is muted just because the number of folks we have. And so that's why we ask people to submit their questions written, and then if we really, if it makes sense, we can unmute individuals and then we let them know.
Sounds great. Okay, well, if there's not any questions, the second part of my talk is really to give you a little bit of a window into the daylight as a light source, or thinking about the sky as a light source. And so when we think about daylighting, one of the great things about it is that it's incredibly variable, right? This is the sort of his horizontal thousands of lux across time on a typical day. And what we see is it's clear in the morning, and you can see the light levels just start cranking up and get all the way up to 40,000 lux here. And then we start to get a few clouds, and they start to shift the brightness. And you can, anyone who's been in a space where clouds are passing by, you see that sort of swell of light. And we see that happening here. We go into cloudy, it gets overcast and gets darker again, which is kind of interesting and makes the space really dynamic and connects it to the outside. But it also reflects a pretty big challenge, because generally for most of our visual tasks, we're trying to maintain a certain level of illuminance, generally down in this range here, somewhere in the 300 lux or 30-foot candle, maybe 50-foot candle range, depending on what the visual tasks are likely to be. And it's a real challenge to do that, to maintain a fairly consistent light level with something as dramatic as daylight, using a fixed object, which is a building. And I'm going to kind of talk about the building as a luminaire, right? Thinking about daylight as your light source and your building as a luminaire that controls it and distributes it in a way that's useful for building occupants. So the three pieces that constitute the amount of light that we see in a space are the sky component, right? That's how much of the sky a point sees. And if we trace this point back under the eave here and over the top of this building, we're seeing this much of the sky's brightness contributing to the point here. The second thing we have is the external reflected component. So that's objects in daylight on the outside bouncing light back to that point. And the third thing is what I call the IRC, the internal reflected component. That's the effect of the interior surface finishes, the shape of the apertures, the furniture, etc., all contributing to how much light is in that point. So conceptually, we can think about that as, what does the sky provide? What does our window provide? And then what does our room do in terms of balancing that brightness? This is a single-sided classroom at a university building in Oregon, where we've got lots of brightness here, and we're trying to bring that across the section and provide a little bit of uniformity, and these sunshades are trying to do that. But that's really our external reflected component, our sky component, and our internal reflected component working together to create a lighting scene. So to understand from a design perspective what you want to prioritize in terms of responding to the different types of sky conditions, this is a good map to look at, which essentially tells us how many cloudy days we're likely to have. And here we obviously in one of the more cloudy regions of the country. And that says if we're going to design for daylighting, we really need a space that works in the overcast. And for Seattle, for example, 70% of daylight hours are likely to be cloudy. So if you're designing for daylighting, the first thing you want to do is make sure your space works under overcast sky conditions, and then secondarily design around controlling direct sun. It's the exact opposite once you get into this part of the country, where we have much more clear days than we have cloudy days, where we want to design our illuminance in the clear sky, and then do the best we can to make it work on overcast days. So that's about setting priorities. So let's think about how we deal with the direct sun. So we've got two things that come out right away. Is on our, so this is south here, where the sun is arcing here from morning through the day to afternoon. I just traced the equinox. And what we see is every single day we have low angle sun on the east side and low angle sun on the west side. And as a daylighting designer or an architect or somebody trying to deal with sun control, low angle sun is inherently problematic, because that's what gets deep into the space. It gets into our eyes, it causes glare, can cause overheating, and can certainly provide for visual discomfort and overlighting. But when we look to the south, we can see that the sun is in a fairly fixed position of the sky, right? It stays in a pretty consistent part of the sky over the course of the day. And then on the north side, we have very limited direct beam sunlight during typical occupied times. So those facts about the way that the relationship between the sun and the earth give us some tools that we can use to design effective daylight in buildings. And just to recap that, I'm going to show a quick video. Can everybody see my QuickTime video on screen? Yeah? Hope so.
Showing, yep. Yep.
Okay. So this is a video that was created on a device that we have called a Heliodon, which simulates the patterns of direct sun. And you can see here over the course of time, you can see that the light distribution's changing pretty radically. We've got patches of direct sun that move and ebb and flow through the space, which isn't too problematic until you get to this point, where the camera view here is now in one of those patches. So when you see a patch of direct sun, can be kind of interesting to look at and maybe dramatic, but you don't want to be inside in that space, because you get that line of sight to the disk of the sun. And this isn't actually the sun, this is just a theatrical spotlight. But it illustrates how, one, dynamic the light distribution is, and two, how problematic it can be when the sun enters our field of vision. So knowing that all of this sunlight would have to be controlled if these were areas where critical visual tasks were taking place. So a great example of of a building as a luminaire is this library which was designed all the way back in 1963 by Alvar Aalto. And his approach to daylighting, I think, is very instructive for us. So the first thing he does is elongate the building in the east-west direction. I talked about east and west being problematic as far as low-angle sunlight. So this building is stretched in the east-west direction to give us mostly south-facing windows here and mostly north-facing windows here. And Aalto just eliminates the problems with direct sunlight by making the east and west windows totally opaque and not having any windows there, so we don't have that low angle sunlight to worry about. The second thing he does is create a very thin plan so that it's easy to daylight both the north side and the south side of this library space from the perimeter, with the exception of this one reading room space, which is really deep, and that's what you see here. And in that case, Aalto's trying to really manipulate the sunlight to effectively illuminate the building. So we've got this big clear story with some fins that you see here. The sunlight strikes those and washes this wall, which then in turn reflects the light back down in between each of these book stacks and takes what would be harsh direct sunlight, creates surface brightness on the ceiling, and then good ambient diffuse brightness down below, reducing the contrast between the clerestory and the window here. So that provides essentially a ring of brightness here, and this is like the angle of the sun in the morning, this is the angle of the sun in the afternoon, and so this space is catching that sunlight all day. But Aalto knows that if he just creates brightness here, the space is going to feel like a cave because it's going to be very contrasty from one side to the other. So he cuts this little window up here and then creates this lighted surface plane for that light to wash on to provide a nice balance of brightness from this side of the space to this side of the space here. And I think intentionally kind of peels back this in a concave way so that there's deliberate brightness in this part of the ceiling plane that by contrast makes this surface seem brighter and this surface seem brighter. So really this building is shaped around delivering, taking direct beam sunlight and turning it into functional diffuse daylighting that's appropriate for the library tasks that are happening. So anybody questions on that, sort of shaping buildings around the sky as a light source?
No written questions, Chris, and you're still sounding good.
Good. So we're about halfway through, and I wanted to talk about some basic rules of thumb that you can use or think about when you're either designing control zones. I know some of that is mandated by code descriptions of diffuse daylighting, but I think when we're thinking coherent lighting scenes, sometimes we have to scratch the surface a little bit deeper. So an obvious rule of thumb that you'll hear a lot and is true is that the daylight distribution from the side is about 2 times the head height of a window. So we've got about 10-foot window height here, and we've got about a 20-foot distribution of daylight into the space. After that, it really tapers off. We also see the effect of vertical obstructions creating deep shadows in the space because our light is essentially traveling almost entirely horizontally, which can be effective, but is very subject to any obstructions in the vertical direction radically changing it. You can see how this partition, the window side of it, really starts to pick up that brightness and collect it there and cast shadows again deeper into the space. So if we think about strategies for controlling glare and managing direct beam sunlight from exterior to interior, we're going to step through this set of sort of window approaches for side lighting, from automated exterior shading systems to interior window coverings to high performance glazing and manual interior shading systems. So one strategy I really like that has some uptake here in the Pacific Northwest is automated exterior blinds. And we see those in some countries, especially in Europe, where there's not a widespread use of mechanical cooling. And one of the reasons we've seen uptake of this in the Pacific Northwest is that with automated exterior Venetian blinds, you can essentially eliminate cooling while still providing comfort in Pacific Northwest buildings because our climate is so mild. But essentially what automated blinds do is they provide 100% sun control and glare control on days when it's clear and when sun is present on that side of the building. They're essentially pre-programmed, and a photo sensor decides, is it sunny or is it clear? And if it's clear, the shades deploy to the slat angle that maximizes daylight distribution while minimizing or eliminating sun penetration either onto the windows or into the space. And then when it's cloudy, they fully retract and maximize the amount of diffuse daylight into the space. So from a performance standpoint, dynamic systems, and this would include, for example, electrochromic windows or interior shades, really give you the best of both worlds in terms of sun control with maximizing diffuse daylight in conditions where sun is not present.
Hey,
Another
Chris,
strategy.
we did have,
yeah.
Chris, we did have a question come in that I want to call out before you go too much further. Is it okay if we take a second to address this question?
Yeah, let's do it.
Oh, great. Okay, a question coming in from Mr. Dan Smith. Dan, thanks for your question. He wrote, why have we gotten away from architects designing daylighting into the space? Does it have to do with the cost of energy? Thanks again for that question, Dan, and I'll let Chris answer.
So let me repeat the question. The question was, why have we gotten away from architects designing daylight into the space?
Correct. And then he asked
think,
specifically, does it have to do with the cost of energy?
Yeah, I think in some ways, probably a renewed consciousness around energy is part of what has brought daylight back as a primary concern for architects. I think for years, starting in about 1940, 1950, when we had low cost electric lighting and there was sort of technological optimism around, we can use technology to solve most of our problems. Daylighting really kind of went away, and we thought, oh, well, we can do it all with electric lighting, so architects don't have to think about that. And it also freed them from the constraints of having to design buildings that comply with the kind of rules of thumb I talked about. They could create essentially any shape they wanted to, and somebody could come in with electric lighting and make it functional for most visual tasks. Now, once there was an energy crisis, there was actually a move toward getting rid of windows because they were thought of as wasteful. But with the improvement of glazing or glass and window technology, architects learned that they could reincorporate daylight into their space and control electric lighting to reduce energy consumption in the space and reduce electric lighting use. Now, with the concurrent or fairly recent, in the past 10 years, 15 years, the widespread adoption of LED lighting, the energy conservation piece of daylight controls has kind of taken a back seat to issues of health and human comfort and research that says if you have a connection to the outside and a view to the outside, you have more productivity, you have better space, all the things that I talked about before. So that's kind of the evolution that we've seen. And daylighting kind of came back as an energy saving strategy, but has stuck around in large part because of the productivity and the qualitative benefits that come around with it, and some of the health benefits that are being documented. Did that answer your question?
We'll have to wait to see what Dan says, but that was a great response, Chris. Thank you.
Yep, thanks. And thanks for the question, I appreciate it. So One of the things that probably many of you have seen is fixed architectural shading. And again, this takes advantage of the sun's position to the south usually. It's most effective that way. And we can see here an overhang in this school down in Tacoma provides full shading of this window, which makes for a comfortable view to the exterior, reduces our mechanical load, eliminates glare, and in this case still allows diffuse daylight to come in over the top of the space, which is managed by an interior light shelf that we see essentially right here. So especially in lower latitudes and especially in south-facing windows, fixed architectural shading can be very, very effective, especially during times of year when buildings are likely to be in cooling mode. So when we're thinking about daylighting, a really important piece of that puzzle is glass and glass properties. And the main attributes of glass that we care about are visible light transmittance, obviously, how much of the visible light in the sky and in the spectrum, the electromagnetic wavelengths that are making it down to our building. How much of that is coming through this, entering the space, and that can be anywhere from, 10% to about 70 to 80% in typical double glass. Generally, for daylight glass, we're looking at low E glazing in the 60 to 65% range. Additionally, we're interested in the solar heat gain coefficient. Most of our commercial type buildings are in cooling mode or want to manage their peak cooling loads. And the solar heat gain coefficient of a piece of glass is a good way to start doing that. And we're generally trying to eliminate or block the sun's solar radiation while emitting the visible light. And then the third thing we want to think about is how much radiant heat transfer can we inhibit. So how much of the, we want to try to keep the heat in the winter and keep the heat out in the summer, and a low U value is reflective of a piece of glass that inhibits that. And generally, we're using what's called spectrally selective glass, and a term that's used to characterize that is the LSG, or the light to solar heat gain ratio. So what percentage of solar heat to light can we emit? And generally a 2-to-1 is about where we want to be. So we want to be able to emit twice as much light to the amount of solar heat that we're emitting with our glass. So we also want to ensure visual comfort. This is a photograph from the old lighting design lab space up on Capitol Hill. And it shows a 10% visible light transmittance fabric shade with direct beam sunlight coming through it. And you can see that there's a blackout shade that needs to come down to provide complete occlusion of the disk of the sun. So we want to make sure that we're selecting fabric shade properties that are effective at, one, emitting some diffuse light, but two, completely providing sun control effectively for the type of activities that happen within the space. So that's another tool in our sun control arsenal. A third is interior blinds, and I like interior blinds because you can see by the shadow lines here, they provide complete occlusion of direct sun while still reflecting diffuse daylight back up into the space. So you're not eliminating the ambient daylight to provide maximum visual comfort in the space. So we talked a little bit about, anybody questions on side lighting strategies or window lighting strategies? Again, the big thing to take away is you've got sort of a couple of daylight zones, one about 1 times the head height of the window, second one about 2 times the head height of the window, and after that, no more daylight. So if you want to have a comprehensively lit space beyond that, we have to think about skylights or top lighting strategies. And a basic layout is that we want to place skylights about on center, the same distance as the height of the space. And this is probably similar to high bay electric lighting with sort of platforms or other types of high bay fixtures, except that we want about half that distance to the perimeter so that we get good surface brightness in addition to ambient horizontal illuminance. And once we know what our placement is likely to be, what we want to do is then decide how big those skylights should be. And the way that I do that is using what's called a skylight to floor area ratio. And here we have a chart that essentially reflects the percentage of skylight area needed to light a floor area. So from 0% skylight area to here about 9% or 10% skylight area in terms of the overall floor area that we're trying to light. And this traces essentially our annual energy savings in kilowatt hours based on those different skylight to floor area ratios. And we sort of peak our optimize around 3% to 4% being the target for our skylight to floor area ratio. However, in places like Seattle or Portland, west of the Cascades, I like to shoot for around 5 to 7%. And I actually give back a little bit of efficiency to get a higher quality and a better sense of brightness in our distribution of light. So I say, you know, my rule of thumb is 3% of the floor area for sunny climates and like 5 to 7 for overcast climates. And what we'll often find in energy simulation is that our best quality daylight may not be coincident with our optimization of energy, but still we're saving significant energy, even though we're giving a little bit back to make sure that we have a very high quality space. And the most important thing to think about when designing for top lighting or overhead lighting or skylights is the employment of light diffusion. And I'm going to show this another little heliodon video. This shows clear skylights in a model of the Boeing 787 facility that was designed for up in Everett about 15 years ago. So we punch a bunch of holes in the sky and let the sun come in, and we get this really dramatic change of light conditions, and it's pretty cool actually. But it's not the appropriate kind of lighting that we're looking for the type of activities that are happening here, where they're doing assembly work and they want low contrast and they want lots of uniformity and evenness over time. So if we take that exact same space and we haven't done anything architecturally, we haven't changed any of the surfaces, we haven't changed the apertures, their sizes, their locations, anything like that. But what we've done is applied a diffusion layer. So essentially just change the glass to essentially diffusing glass. We get this very consistent illuminance. So now the sunlight's being diffused. And rather than having a punch of direct beam sunlight that's moving through the space, we take that sunlight and diffuse it evenly across the space so the light levels ramp up in the morning and then ramp back down at night. But our distribution of light is locked into space pretty similarly to what we would get with an electric lighting situation or with diffuse electric lights. So light diffusion is a very, very powerful tool for top lighting. It's the way to get uniformity, it's the way to get consistency, and it's a great way to avoid glare. So how do we do that? We can use insulated laminated glass with PVB inner layers. That's essentially safety material that makes the glass so that you can't fall through and it keeps shards from falling down if the glass breaks, but it can also be used for diffusion. That's my preferred option. We also have glass sandwich panels. We have fiberglass insulated products, one being Calwall that's well known, or polycarbonates in spaces where you're not super concerned about the thermal properties, at least for this type. There's some that are more thermally insulating, but this is a polygal polycarbonate type material. You see this in a number of big transfer stations or other unconditioned high bay type spaces where daylight is desirable. Another strategy is using light diffusion through refraction, and that can happen through, in this case, the dome of a solar tube, or refraction through a highly reflective tube. Those of you who've been in the classroom in the lighting design lab have seen these in action. Or we can see this through prismatics. So many of you will be familiar with prismatic lenses for luminaires, but we also see that in skylights. There's a company called Sun Optics that focuses on prismatic diffusion of skylights. So anybody questions on top lighting and side lighting? I'm just really scratching the surface of these two approaches, but you know, you kind of put these pieces together and that's how you get a well daylit building. All right.
No other questions that come in, but yeah, sounding good, Chris.
Okay. So here's a project that really, I think, does a great job of putting all of those pieces together. This is a building down in Federal Way, designed by Weinstein AU, the architecture firm here in Seattle. And it consists of a high bay gym surrounded by sort of classroom size game rooms and learning lodges. And it really uses light in a beautiful way to, one, fill the gym with diffuse daylight, really wash the walls and light the vertical surfaces, which is the main thing that you see when you're in the space. And then some selective cuts here on the perimeter of the gym on the outside to light the inside wall of the gym. So we're really lighting both sides of these walls and then bringing light in from the perimeter over here. So let's take a look and see how that works. So first thing you do is you walk into the space. There's this beautiful transparent skylight that lets in a little bit of direct sun here, and provides some visual excitement. And all the electric lights are off in this image, which to me is really impressive. You can see all the way into here with the gym. That's light filled. It creates transparency through that window, like I talked about earlier. There's translucent walls. There's some skylights here that wash this side of the wall. When we get into the gym, you can see that there's skylights here that wash the other side of the wall. So we're really paying attention to how do we graze light onto vertical surfaces. And then we've got these corner clerestory windows, which are translucent. So they don't allow any direct sunlight, but they diffuse light across the vertical surface of the gym this way and back this way to complement what's happening with these skylights that wash the walls here and provide uniformity and brightness over here. And it's only in the very lower windows that we get transparent glazing so that we can see a connection to the outside here and sort of see the landscape. But these windows are low enough and actually face north and south so that the sunlight that comes into the space is very modest. It's just little bits and pieces of it. But here we see the gym with, again, no electric lighting energized in this particular photograph. The perimeter spaces are treated similarly, where you've got skylight here that's translucent that washes this vertical surface with light. And then we've got windows with the little light shelf here and a shading device on the outside that brings light into the space. And it comes back right to about here where the skylights pick up. So even despite the differences in aperture approach, we get really nice uniformity across this gym, good balance from one side to the other, and a nice composition of diffuse daylight. You can see that over here. Here we see the light shelf effect, putting a little bit of light onto the ceiling, darkening the perimeter just a little bit, so that, again, we provide a little bit more uniformity across the section and we can see into the gym here.
Hey, Chris,
and then
we had a
just
question
another
come
shot
in.
of, yeah.
question here is, for the slide on energy savings from skylights as a function of skylight area, are the savings significantly different? Are the savings significantly different by building use or thermal performance?
Yeah, that's a great question. So that's from a tool called SkyCalc, and yes, you can put in different program types. So, for example, a building with tons of internal loads is going to perform differently than one that has some beneficial heating from skylights. The model that was derived from also used acrylic dome, and so if you used a higher performing skylight like glass, the thermal interactive effects of the savings would be different. But that particular tool does use essentially it aggregates all the. Let me go back to it. It says something like in the title. There we go. So this is total energy savings from skylights from lighting, cooling, and heating, all converted to kWh. And this is a little bit, some of the assumptions in here are older. I think the lighting power densities were like 1 watt per square foot. So some of the cooling penalties will be a little bit less, and some of the heating penalties will be a little bit more than a facility today. But yes, absolutely. You would, in the tool, there's a pull down menu and you can pick sort of warehouse or office or what have you. And the savings would change based on that, based on internal loads, and also would change if you were able to change the skylight to a higher performing glass skylight, which is generally what I recommend today. That was a great question though. That's another topic that you can go quite deep into, looking at the trade-off. And as I said, a lot of times I'm gonna maybe not take the most optimal energy savings if it means having to sacrifice some of the space quality stuff. Obviously, I'm not gonna create spaces that have create spaces that have significant energy penalties to make the daylight work. But I might take a little bit of a hit on the energy side, maybe not fully max it out if it means improving the quality significantly. So those are all value judgments you have to make in the design process. So I'm gonna speed up. Here's a couple of pictures of some the shading system and the light shelf. I think these are pretty elegant. It's kind of cool with sailcloth. It just shows that you can use a lot of materials and creativity. So I'm gonna skip the controls piece because I want to move ahead. In general, you guys have all gotten this probably from classes from Sean. If you haven't, you should register and get it. And I'm sure it's part of this sequence. Learning about controls integration. Couple things in the past, we used to have on-off switching, which would cause people to get up on ladders and disconnect things or put Dixie cups over the sensors. Now we have nice, smooth, continuous dimming that's essentially transparent to the occupant. And these are some key components: the window, the sensor, the controller, a dimming ballast, and a fixture. And you can, with luminaire level lighting controls, to make it really simple, all of that stuff is onboard, embedded, and essentially ready to go out of the box. And LDL has great classes on next-gen lighting controls of all sorts. So I'm gonna jump over that and get into some tools and resources so that we have some time for questions.
Hey Chris, speaking of questions, could we take another one real quick?
Yeah, let's do it.
Okay, awesome. Question coming in from Jenny. Is the amount of foot candles in a space significantly different when using translucent skylights as opposed to transparent?
Yeah, so that's a really good question. I'll go back to the video. So let me get my transparent. So if we measured our horizontal illuminance, maybe our average might stay the same, right? But the thing that's different is we might have 1,000 foot candles here, or 5,000 foot candles here, and maybe 10 here, right? So the foot candles that you would measure here of sunlight could be, yeah, it could be as high as 5,000 foot candles or even more on a clear day. And so this area has tons of foot candles and this area has much much lower, maybe, you know, even 4 or 5 over here. Where if we go to translucent, what we would see is much higher uniformity, where we get, let's say, you know, I'm just making up numbers, but 100 foot candles here, 50 here, 30 here, 50, and then back to 100. Where here we went from like 5, 6, 7, 5,000, 10, you know, maybe 100, and then back to like 2 or 3 over here. So in terms of the amount of light coming through, it's generally going to be the same. The difference is it's going to be much more evenly distributed. So foot candle wise at various points are going to be radically different.
So Chris, so kind of follow up to that, the question or the follow up is, so you're not losing any in the material? Question mark.
Yeah, that's a great question. So to dig in a little deeper, yes, you would be losing a little bit, because what happens is, well, it depends on what you're using for your technology, but I'm going to use glass, for example. So a low E double glazed unit with high performance glass would probably let in about 63% of the visible light into the space. Now, if I design that same assembly with a diffusion layer, that diffusion layer is going to reflect some of that light back, and our total visible transmittance is going to be more like 50%. So we're going to give up maybe 10, 15% of visible transmittance to get that. Now, if we used a prismatic skylight, for example, you can get those in visible transmittances of 70 or 80% almost. The difference is that the thermal properties of them are not quite as good. So it gets back to the technology, but I would say, you know, for equivalent thermal and solar heat gain properties, you probably give up just a tiny bit of visible light transmittance to go to diffuse. Hope that answered the question.
Great, thanks, Chris.
If people want to talk specifics about glass, I'm happy to chat offline. You can send me an email. My email is going to be on the, it was on the first slide, and it's also going to be on the last one. I'm happy. I could go on forever on glass. So let's talk about some resources. So I've worked with the University of Idaho to build a tool called the Daylighting Pattern Guide. And that tool essentially takes what I think are the top roughly 20 daylighting conditions you might experience when designing a building, and stepping through some common simulation scenarios that architects and engineers might come up with. And it's drawn from buildings over a wide geographic and climate diversity. And it's a free website. You can go online. You have to register, but you never get any spam or emails from it. They're just tracking usage on it to see that it gets used and people think it's valuable. And what it does is it describes the pattern of the daylight scenario, and then it steps through a series of narrated conditions that you might design to, and provides photometric and luminance-based feedback on the different designs. And what we did was we documented physical spaces that were deemed really good daylighting designs using the simulation tool Radiance to create essentially a calibrated model. And then this is a false color data from our calibrated model in the actual site visit. And then steps it through from not being very good from being not enough windows or not enough apertures to having too many. And this is a classroom. So for example, if we have a really small corner window here, about a quarter of our classroom is lit. And we increase the ceiling height of that, and it bumps up to about half the classroom. And then we put a window in the back, it starts to fill in. And then we add some skylights, and we have a near 100% daylit classroom. And you can just sort of see how this goes from a dark space to a brighter space to, in some cases, an overlit space. So here's some different clear story geometries. Here's another pattern that shows the impact of interior furniture design. So we've got an architectural space. It's pretty well daylit. If you simulate it, the green is good. The line of green is good. The blue is starting to get a little bit too dark. And we've got a pretty well daylit space, a nice green bright wash on the ceiling, good back wall vertical surface brightness to balance the section, and everything looks pretty good. Our horizontal illuminance drops below 300 lux about here, but that's the corridor in the back of the space. So if we add furniture in it and just some sort of basic collaboration style desks, we don't impact the daylight at all. When we add modesty panels, also not too bad, but our acoustics maybe aren't good, our privacy isn't all that great. So if we add 42-inch partitions, we start to get a reduction in light levels, but we're still about 100% daylit in the workstation zone. When we get up into vertical partitions that are perpendicular to the window, we start losing a little bit, right? We come back and we have a daylit, just about a half of the workstations are daylit. When we go higher, the back of our space starts to get dark. Now we're talking about a real cave type environment. And if we go up to 6-foot partitions, those are at 72 inches, essentially we've got a space where little tiny bit of the aisleways are lit and the rest of the space is quite dark. And you know, maybe we can pull that back by doing some glass partitions or something like that. But the point being is we haven't changed the architecture at all, but as the interior furniture's partition design starts to encroach more and more on the space, we start to lose our daylighting effect. So thinking about how our interior design decisions impact our daylight distribution. And so there's tons of different patterns like that. And I would, you know, I'd encourage you to explore that if you're interested in sort of a narrative simulation-based guidance on daylighting design and likely probabilities of success of different design options. And it's got classrooms and offices and high bay, it's got warehouse, it's got gyms, it's got a whole bunch of different building type configurations that you might be thinking about. So the last thing I want to point to is some IES resources that I think are really good. I was part of a podcast series, and I think these are still freely downloadable from the IES. I did these with Matthew Tanteri and one of my colleagues, Kevin Vanden Melenberg at the University of Oregon. There's a daylighting seminar that gets put on by the LDL here every couple of years. There's an RP5, which is recommended practice for building daylighting. There's the daylighting metrics, spatial daylight autonomy, and annual sunlight exposure, if you want to get into the weeds about simulation and simulation metrics. And obviously the lighting handbook is a great resource for daylighting and establishing lighting design criteria, as well as the handout on controls. So I wanted to leave John at least 10 minutes and give some time for questions too, if any didn't come up in the meanwhile. So I know I covered a lot of material there at the end, and if people want to stick around for questions, I'm happy to do that. And if you want to contact me offline, my email is at the bottom. I'm happy to chat either on a phone call or respond to your emails.
Yeah, that was really awesome, Chris. Thank you so much. I'm not seeing any additional questions, but we're going to leave that up and folks can type them in if they have any. And how about this? While folks type their questions in, yeah, Chris, I might ask you to kind of cue through here. So again, want to give a big virtual round of applause to Chris Meek, our guest speaker, for giving this really awesome presentation, and got just a few quick words from Lighting Design Lab. So next slide for me, please, Chris. Want to highlight these awesome upcoming events that we have on the LDL webinar series. You can click, you'll see the copy of this webpage, a copy of this presentation will be available on our website, and you can register for these classes there. I want to highlight first time ever, we'll be featuring this Fundamentals of Network Lighting Controls online class. It's a two-parter. and you have to register for both if you're interested, but we're really excited to be offering this. That's sort of a introductory to for folks who can't make the in-person class right now. Next slide, please, Chris. We covered this. Information is going to be available, and Chris's information has already been given to you. So visit our website. You can also email us at lightingdesignlab@seattle.gov. And I think we're going to take it out here. Next slide, Chris. Want to give one more big thank you. The Lighting Design Lab, as I said, we are part of Seattle City Light, but the work that we do is made possible in part with additional support from the following 2020 member utilities. So special thank you to these utilities. You know, it's kind of like if you're a utility and you're listening today and you thought there was, you know, value in what you heard here, that's pretty awesome and free to boot. Well, thank you to these utilities who are making it possible. So we want to recognize them and we thank them for their support. And one more slide for me, I think, Chris. We will take it out with, that's all, folks. So as you exit the webinar, please remember to take just 2 minutes to knock out that survey. Chris, I haven't seen any other questions come in, so I'm going to say going once, going twice. We'll let everybody have a little time back in their day, and thank you all very, very much for joining us. We look forward to seeing you for our next LDL webinar on June 2nd, Network Lighting Controls for Utilities and Utility Staff. All right, thank you, everyone. I think we're going to call this a wrap, and the presentation and deck will be available in just a couple days on LDL's website. Thank you.
Yeah, thanks, everybody. I appreciate